Water. Water comes in many forms: groundwater, surface water, drinking water, wastewater, stormwater, or dual use and reuse. Some may need greater treatment than others, depending where it is discharged or on how it is used. In the end, however, it is all water. This program is meant to be a general wastewater overview that will also discuss pre- and primary treatment and how the liquid stream is separated from solids before continuing to secondary treatment. Understand that no two treatment plants are identical, and that while there are variations between treatment methodologies and plant designs, usually because of the region or climate, the science and concepts remain the same. Wastewater is the used water from a community, including water from industrial processes that flows to a treatment plant. Most people refer to this as sanitary sewage, but wastewater can also come from nature. Stormwater, surface water, and groundwater infiltration may also contribute to the water that enters a wastewater treatment plant. According to the U.S. Environmental Protection Agency, the average American produces approximately 100 gallons of wastewater daily. A Water Research Foundation report on residential use found 26.7% was used for flushing toilets, 21.7% washing clothes, 16.8% bathing, 15.7% faucet use, leaks 13.7%, and 5.3% is other uses. As you can see, residential wastewater is in fact mostly water. It averages 99.9% water by weight, and a very small percentage, 0.1%, is waste. This small percentage is typically referred to as total solids. Total solids are a combination of dissolved organic and inorganic solids and solids suspended in the water. Both are removed in the wastewater treatment process, but removing that very small dissolved solids portion is the focus of wastewater treatment. Wastewater treatment speeds up what happens naturally in streams and rivers. In these waters, bacteria and other small organisms will feed on waste, eliminate waste, and produce new bacteria cells, carbon dioxide, and other products. These waste-eating bacteria consume oxygen during this process. Aquatic life needs oxygen to survive. Nature's balance is tipped when the amount of untreated wastewater exceeds the natural water's ability to purify and ultimately support aquatic life. One location where pollution has intersected concerned citizenry is the Willamette River in Oregon. According to the Oregon Environmental Council, over the past 80 years, the Willamette River has been polluted by industry, agriculture, and cities. In 2006, American Rivers listed the Willamette as the third most endangered river in the United States. Industries continue to discharge wastes into the river under authorized permits. Attention is being drawn to permits that allow mixing zones, areas where pollution is allowed to exceed water quality standards until it mixes with the receiving stream and becomes diluted. A 6-mile stretch of the river in the Portland Harbor is now a federal Superfund site. This area is highly polluted with toxins, heavy metals, and other substances, and the cleanup will likely take a decade. Protecting our waterways requires vigilance of not only the pollution created in homes and by industry or point sources, but also the pollution collected as snowmelt and rain runoff parking lots, parks, and farm fields. This latter is known as non-point source pollution and can contain such things as sediment, heavy metals, herbicides, animal waste, oil, and grease. Wastewater treatment helps keep the point source pollution out of our rivers and streams. In 1892, only 27 American cities provided wastewater treatment. Over a century later, more than 20,000 publicly owned wastewater treatment plants operate in the U.S. and Canada. According to the EPA, over 75% of the U.S. population is served by centralized wastewater collection and treatment systems. The remaining population uses septic or on-site systems. The Clean Water Act and the Canadian Environmental Protection Act established the foundation for wastewater discharge control. The primary objective of the Clean Water Act is to restore and maintain the chemical, physical, and biological integrity of the nation's waters. It established a control program for ensuring that communities have clean water by regulating the release of contaminants to our country's waterways. Permits that limit the amount of pollutants discharged are required by all municipal and industrial dischargers under the National Pollutant Discharge Elimination Systems, or NPDES permit program. Remember that in drinking water treatment, the idea is to protect the public health. In wastewater treatment, the focus is to protect both the public and the environment. In their book, Solving Sewage Problems, George Fuller and James McClintock summarized waste disposal practices in the Americas and the impact of the population transitioning from rural to urban residents. In early days, each household disposed of its filth as best it could. Cesspools for household wastes were officially recognized by sanitary authorities, and there was little or no supervision of the disposal of the contents. Household wastes in increasing proportions reached the watercourses. The resulting nuisances became a serious problem about the middle of the last century. The sewage problem thus took its modern form of pollution of waterways. However, sewers were not the solution to waterborne diseases. In many cases, it was the problem. While they moved human wastes out of urban areas, they were dumping the untreated waste into streams and rivers that were also used downstream for drinking water supply. The infected fecal matter containing cholera or typhoid re-entered drinking supplies and caused epidemics that swept across Europe. In 1853, several outbreaks of cholera spread through England, with London being the hardest hit. By fall of that year, over 500 people had perished, and in some neighborhoods, the death toll had risen to 12.8%, more than double the rest of London. An English doctor, John Snow, observed the cholera epidemic of 1853 and attempted to find the root cause of one particular virulent neighborhood outbreak. Snow used rudimentary scientific method, microbiology, and accumulated social statistics, such as death certificates, to trace the localized spread of cholera. His deduction led him to a single water pump in the Broad Street area. The pump handle was disabled, and the deaths subsided. Snow deduced that sewage-contaminated water was the carrier of an agent that caused cholera. Because of his work, Dr. John Snow is widely considered the father of epidemiology. Many early sewer systems collected stormwater and sanitary wastewater in a single system. These combined sewers helped prevent flooding in cities but overwhelmed treatment plants, and in some cases released pathogens and other pollutants during excess flow events. Today, the most common form of pollution and/or wastewater control is through modern wastewater transmission systems or sewers that collect and convey wastewater to the treatment plants. Sewers are below-ground conduits, usually large pipes or concrete forms, that use gravity flow to transport domestic and industrial wastewater from urban areas to treatment plants. Sanitary sewers need to be located below the frost line and deep enough to receive outflow from residential basements. Methods of conveyance typically include gravity systems, force main systems, vacuum systems, siphons, or a combination of all three. A force main is where wastewater is pumped under pressure rather than using gravity flow. The U.S. EPA estimates that there are approximately 500,000 miles of publicly owned sanitary sewer systems in the U.S., and by the year 2000, approximately 208 million people in the U.S. were served by centralized collection systems. Measuring the flow and loadings to the treatment plant is important for plant operations and capacity planning for both the collection system and the treatment plant. The total amount of wastewater entering the treatment plant is called the hydraulic loading or flow. Open channel flow and full pipe are two of several methods measuring collection system flows. Plant loadings measured as the headworks of the plant give the operator a picture of organic and inorganics that the treatment process will have to remove. Here are some essential terms and abbreviations operators should know. Solids, total solids abbreviated as TS, total suspended solids or TSS, biochemical oxygen demand or BOD5, and chemical oxygen demand or COD. Solids refer to matter suspended or dissolved in water or wastewater. Solids analyses are important in the control of biological and physical treatment processes and for assessing compliance with regulatory agency wastewater effluent limitations. Total solids are a measure of all organic and inorganic solids in the wastewater. There is standard laboratory testing that is done to determine total solids in wastewater. TS is usually measured by evaporation of a sample and the subsequent drying at a defined temperature to measure the solids that remain. Total suspended solids are a measure of the suspended solids within a mixture. Suspended solids are visible and in suspension. They include paper, grit, rags, plastics, etc., and can be removed by physical or mechanical means like sedimentation or filtration. TSS are further classified as inorganic and organic. Inorganic substances are inert and not subject to decay. They can include a number of potentially toxic elements such as arsenic, cadmium, chromium, copper, lead, mercury, zinc, etc. Typical domestic wastewater is composed of about 50% organic material which will decay or decompose through bacterial activity. Among the organic substances present are carbohydrates, lignin, fats, soaps, synthetic detergents, and proteins. Biochemical oxygen demand, or BOD5, is the dissolved oxygen demand required of microorganisms for decomposition over a 5-day period. Or more practically, it is the measure of the organic composition of wastewater. Organics contain carbon, hydrogen, and oxygen and will decay or decompose through bacterial activity. These tests are used to determine the approximate quantity of oxygen that will be required to biologically stabilize the organic matter present. BOD5 is also used for compliance. The amount of influent wastewater flow is usually measured in million gallons per day, or MGD. It can be called hydraulic loading rate only if you have the unit area, because the unit area is rarely known for a treatment plant. The hydraulic loading rate is typically a process control parameter used for unit processes like sedimentation, flocculation, etc. The COD, or chemical oxygen demand, is the amount of chemically oxidizable matter present in wastewater. COD is always higher than BOD. The treatment processes used for wastewater can be segmented into the following categories: preliminary and primary treatment, secondary treatment and disinfection, and solids handling. This program will cover preliminary and primary treatment. Pre-treatment processes equalize flows and loadings, and precondition wastewaters to neutralize or remove toxics and industrial wastes that could adversely affect sewers or inhibit operations of publicly owned treatment works. Preliminary treatment processes protect plant mechanical equipment, remove extraneous matter such as grit, trash, and debris, reduce odors, and render incoming sewage more amenable to subsequent treatment and handling. Primary treatment employs mechanical and physical unit processes to separate and remove floatables and suspended solids and to prepare wastewater for biological treatment. Odor control is an issue with wastewater. Pre-aeration and pre-chlorination can help maintain an aerobic state and keep the wastewater from going septic, thus reducing odors. Additional benefits include reduced corrosion by stripping off hydrogen sulfide and improved solids separation and settling by agitating the solids to release trapped gases. The agitation of wastewater in the presence of air tends to collect or flocculate lighter suspended solids into heavier masses, which settle more readily in the sedimentation tanks. Pre-aeration also helps to separate grease and oil from the wastewater and wastewater solids and to carry them to the surface. Pre-chlorination can achieve similar results. Hydrogen sulfide is responsible for the rotten egg odor that comes from septic, anaerobic wastewater. Sulfates in wastewater break down into H2S, which is heavier than air and will collect in manholes, pits, etc., posing a safety hazard and odor problems. H2S is toxic, and all safety precautions are essential. Wastewater entering the treatment plant, or influent, flows through a first step called preliminary treatment. This step removes the solids that could damage pumps and clog pipes and cause undue wear on equipment. The preliminary process consists of screening, grit removal, odor and flow control, and equalization. Screening removes large objects such as rags, sticks, plastics, and rocks. Bar screens, drum screens, or passive screens are the most common. Large screens can be cleared by hand, but usually a mechanical rake is used to keep them free of the miscellaneous debris called rags. The collected materials are then dewatered and the solids are taken for disposal, usually at a landfill. Fine screens are cleaned by brushes and/or a water sprayer. While screening is widely used, some plants employ grinders or shredders to churn the rags into very fine particulate matter that can be removed later on in the process through settling basins. In some plants, shredding devices are installed after the bar screens or as alternatives to screening. Shredding devices reduce solids to a size that can enter the plant without causing mechanical problems or clogging. Smaller materials such as grit and sand are removed in the grit chambers. Grit is any fine particulate matter, including sand, coffee grounds, etc., that must be removed before the liquid stream enters the main treatment plant. Unabated, grit can clog pipes and destroy pumps, so its removal is imperative. According to the US EPA, grit is traditionally defined as particles larger than 0.21 millimeters or 0.008 inches with a specific gravity greater than 2.65. In most wastewater plants, the pre-treatment equipment has been traditionally designed to remove 95% of these particles. The most common and least expensive way to remove grit is through gravity. Grit chambers are designed to slow the influent flow enough to allow gravity settling of the heavier grit, gravel, and sand particles. The grit is removed from the bottom of the grit collection chamber, dewatered, washed, and conveyed to a disposal site. Floating particles, often plastics, and scum are skimmed from the top of the basin, while the lighter weight constituents remain in suspension. Another method for removing grit is a velocity system that uses centrifugal force to separate the liquid from the solids. The solids are extracted from the outside edge of the spinning mass, while the liquid stream flows up and out from the center of the chamber under pressure. Not all of the materials to be removed are on the bottom of the tank. Pre-aeration also helps to separate grease and oil from the wastewater and wastewater solids and to carry them to the surface. As the flow passes out of the grit chamber, it goes on to primary treatment. Primary treatment involves a more advanced settling basin called a sedimentation tank or clarifier. Here, the wastewater flow is slowed down considerably from minutes to hours in order to settle and remove the smaller solids and skim off oil, grease, and other floatables that were not removed in the grit chambers. The core concept behind the sedimentation process is the decreased velocity of the water carrying the solids. The faster the water enters the sedimentation basin or clarifier, the more turbulence is created, and the more suspended solids are carried into the treatment system. This is why it is important to understand the flow rate. At the very end of this program is a review of some of the math used in water treatment. The wastewater enters the clarifier, the speed of the incoming water is slowed, and the water evenly distributes around the tank. The point is to introduce the wastewater into the clarifier as quietly as possible. The higher the flow rate, the greater the turbidity and the greater the solids flowing over the effluent weir, rather than settling out as solids. Most sedimentation basins have 4 zones. The influent or inlet zone decreases the velocity of the incoming water and distributes the flow evenly across the basin. The settling zone provides the calm area necessary for the suspended material to settle. The effluent zone provides a smooth transition from the settling zone to the effluent flow area. It's important that currents don't stir up any settled solids and carry them into this area. The final zone is the sludge zone, where settled solids are separated from other particles in the settling zone. There are many variations in design for sedimentation basins. The 2 most common types are rectangular and circular clarifiers. In a rectangular clarifier, water flows across a rectangular basin. A circular sedimentation basin is fed from the center, and water flows to the outer edge of the basin. There are many alternatives to traditional sedimentation, including high-rate and upflow clarifiers. These variations in design are generally used to reduce detention time, increase flow rates, and raise capacity within a smaller footprint. All clarifiers use weirs and water overflow to separate the less turbid water. A weir is like a small dam, gate, notch, or other barrier placed across a basin to help regulate water out of a basin. The weir overflow rate is used to determine the velocity of wastewater over the weir. The velocity informs the operator about the efficiency of the sedimentation process. At constant wastewater flow, the shorter the length of the weir, the faster the water velocity will be out of the basin. Conversely, the longer the weir length, the slower the velocity will be out of the basin. The goal is to remove the majority of total solids from the water, even if that means multiple clarifiers or recycling the water back through the clarifier more than once. Once that is accomplished, liquids flow one path and the sludge another. Sludge can be removed at intervals or continually removed by mechanical scrapers installed to scrape the sludge away. The solids removed from the bottom of the clarifier or sedimentation tank are called primary solids. These solids are further handled at the plant through dissolved air flotation, digestion, and disposal. The sludge can be placed in lagoons or on sand beds where it eventually dries out. It can be dried by mechanical dewatering techniques. It can be sent to a treatment plant for processing. Attention must be paid to how long the flow remains in the basin. Too long, it goes septic. Too short, inadequate removals. This solid-liquid separation process removes upwards of 90 to 95% of settlable solids, 40 to 60% total suspended solids, and 25 to 35% BOD5. So at this point in our wastewater treatment, the majority of the solids have been removed and the 2 streams, liquids and solids, move on to secondary treatment, or BOD5. The following section is a review of math techniques that can be beneficial to wastewater treatment operators when computing sedimentation. Mathematical tools available to operate and control the sedimentation process are Stokes' law, surface overflow rates, weir overflow rates, and detention time. This is an equation called Stokes' law. It calculates the rate of fall of particles through a liquid medium. There's a lot of math behind determining how suspended solids settle out of water, but what we need to know to operate a clarifier is pretty simple. The water in a clarifier needs to be slowed down enough and held long enough for flow to settle to where clarified water can be collected from the top of the basin. As an operator, you'll need to determine whether your flow rates are within the range of your sedimentation process design. Setting Stokes' law aside and making a few assumptions, we can work with a simplified equation. The settling velocity is determined by the flow through the basin divided by the basin surface area or surface overflow rate. Notice that the depth of the sedimentation tank or clarifier is not a consideration in the calculation of surface overflow rate. Overflow rates depend on settling velocity of the flow or is equal to the settling velocity of the smallest, lightest particles being removed. Let's start with determining the surface overflow rate. A water treatment plant has a daily flow rate of 4.8 million gallons per day. The rectangular sedimentation basin is 120 feet long, 40 feet wide, and 8 feet deep. What is the surface overflow rate in gallons per day per square foot? The surface area is 120 feet by 40 feet, which equals 4,800 square feet. 4.8 million gallons per day divided by 4,800 is 1,000 gallons per day per square foot. Now let's apply this equation to a circular center feed clarifier with a diameter of 55 feet and an influent flow of 2,075,000 gallons per day. This time we're dealing with a circular surface area, so we'll need to use pi. You'll recall that the area of a circle can be calculated by pi times the radius squared. Pi is commonly rounded to 3.14 times the radius, which is half of the diameter, 55, or 27.5 squared. This gives us an area of 2,375, and the units are in square feet. We know the flow rate is 2.075 million gallons per day, so we take 2.075 million and divide by 2,375 square feet, which results in a surface overflow rate of 874 gallons per day per square feet. The weir overflow or loading rate is a lot like the surface overflow rate, except instead of looking at the basin as a whole, we are interested only in determining how fast the water is flowing over the weir. This is important in identifying high velocities near the weir, which adversely affects the quality of the effluent. The weir loading rate, or WLR, is equal to Q, the flow, divided by L, the length of the weir. Weir loading rate units are typically gallons per day per foot or liters per second per meter of weir. There are a number of weir configurations. Sometimes there is a single weir on the effluent of the basin, but there can also be double-sided and even multiple weir configurations. The total length of the weir is the important factor, however. A double-sided weir really just doubles the weir length, reducing the weir loading rate by half with no change in flow rate. Let's look at an example of a circular clarifier where the flow, or Q, is 3.6 million gallons per day, and the diameter of the clarifier is 80 feet. To determine the weir loading rate, we first need to determine the length of the weir. The length of the weir is equal to the circumference of the circular clarifier, or 2 times pi, times the radius of the tank. The radius is 40 feet. 2 times pi times 40 feet equals 251.2 feet of weir length. We can now plug the weir length into our formula. Flow rate of 3.6 million gallons per day divided by 251.2 feet of weir equals 14,330 gallons per day per foot of weir. 14,000 gallons per day per foot is within normal operating range. Let's look at another example, except this time we'll use metric units and we'll solve for per second instead of per day for the time factor. We have a sedimentation basin with a weir length of 25 meters and a flow of 40.5 liters per second. Weir loading rate is 40.5 divided by 25 meters of weir length, which is 1.6 liters per second per meter of weir. Now consider a circular clarifier that has a continuous weir around the perimeter or outside edge. The tank diameter is 60 feet with a flow of 1.87 million gallons per day. So let's determine the weir loading rate. We find the length of the weir by calculating the circumference of the circular clarifier. 2 times pi times the radius. 2 times 3.14 times 30 feet is 188.4 feet of weir. 1.87 million gallons per day divided by 188.4 feet of weir results in 9,926 gallons per day per foot of weir. Communities with good wastewater systems are communities that can continue to expand and grow by protecting public health through robust wastewater collection and treatment systems.